Today's topic will be rates of reaction. This is the first out of 2 videos. Let's look at our objectives for today. First, we need to define the rate of reaction, identify the factors which affect the rate of reaction. Those are concentration, temperature, surface area, and the presence or absence of a catalyst. So I always like to see the relevance of whatever topic we are studying. So let's take, for example, these following reactions. All of these are everyday reactions. The first one is ripening of apples. This is a reaction that takes place over a period of weeks. We have the maturing of cheese, which can take months. The burning of fossil fuels can take hours or even minutes. And explosions, which take place in fractions of seconds. Right? So these are all everyday reactions, which shows you how important rates is in everyday life. So let's think about if an apple were to take 10 years to ripe. Wouldn't you think that's a problem? So every day, scientists are always looking for ways to improve the idea of rates of reaction, or they try ways to control the rates of reaction. So what is rates of reaction? The rate of reaction is a measured change in the concentration of a reactant or product with time at a stated temperature. So take, for example, this, all right? So these white molecules here and the red molecules on this side, these are reactant molecules. As they react, they form products. So as the reaction takes place, we have more products forming with time, and we also have less reactants with time. So what we also need to do is understand something called the collision theory. This is really the science behind reactions. So in order for a chemical reaction to occur, reactant particles must collide with each other to form products. Not every collision results in product formation. In order for products to be formed, reactants must collide. They must have enough energy upon collision for bond breaking, and they must also have an appropriate orientation. These 3 factors are very important, and no reaction will take place unless we have every one of these. And every one of these will result in a successful collision, which results in the formation of products. This diagram here is called an energy profile diagram. This shows the energy of reactants before the reaction takes place. Now, reactants must gain a certain amount of energy in order to collide and form products. If the reactants do not reach this activation energy, it will not react. Once it gains this activation energy, it collides successfully and then releases energy to form products. You'll see more about this reaction profile in our next topic. How is rate measured? Firstly, you can measure rate by measuring the concentration of reactants with time or the concentration of product with time. So let me give you an example. Here we have a reaction taking place in a conical flask. As the reaction is taking place, a gas is being evolved. And when the gas is evolved, it loses mass. So this is before 183.62. This is after. So it lost mass. Our measured change here is mass, and we will be timing how this is changed. right? So these are two ways we can calculate rates of reaction. You can either calculate using the decrease in concentration of reactant or the increase in concentration of a product. However, this is not always easy to do. So there are other ways of determining rate. So one can be measuring the volume of product formed. For example, we can collect the volume of gas produced, for example, in metal and acid reactions. So in a metal acid reaction, we have hydrogen being formed, and at time equals 0, you will have no hydrogen. We can time for every minute how much hydrogen is being formed. If the gas is allowed to escape, measure the mass of the reactant. That is what I just showed you in the previous slide. You can also look at the appearance of a precipitate. For example, there's an experiment called the disappearing cross experiment, where you measure the time it takes for a cross to disappear. You can also measure changes in color. For example, between potassium iodide and hydrogen peroxide, you see a brown color being formed. And you can also note changes in temperature, pH, or pressure with time. The key here is measuring any changes with time. So let's look at this in a little more detail. So let's say we add some magnesium to a conical flask containing hydrochloric acid. What will happen is that hydrogen gas will be formed, and we are going to time the volume every minute. So when we get those results, we are going to plot a graph of volume of hydrogen gas formed versus time. When we plot that graph, it's going to look something like this. So over here, we'll see a very steep line, and then eventually it flattens. All right, so let's look at the actual figures here. So the rate of reaction is the increase in volume of hydrogen, which is the product, divided by the time taken. So at 1 minute here, 60 seconds, our volume of hydrogen gas produced is about 28 cm cubed. So 28 divided by 60 gives you 0.47. This is the rate at 1 minute. Now the rate at the second minute, right? We're not going to take all of this. We're only going to take the difference between the first and the second minute. So that difference will be 10 cm cubed. And when we divide it by the time, which is still 1 minute, it's 0.17. Now, if you look at the difference, you can see that this rate is faster than this rate. What that says is that at the very beginning of the experiment, right, the rate is faster, and then it slows down until eventually it stops. So at 3 minutes, you see the volume of hydrogen gas produced is 45 cm cubed. After this, no more hydrogen gas is formed. So at this point where it flattens, you can say it has stopped reacting. Here's another example. This is just like the first one I showed you. We can measure the rate of change of mass of the reactants with time. Right, so let's say it's between calcium carbonate and HCl. You get calcium chloride plus carbon dioxide and water. We will be losing carbon dioxide gas here. So as carbon dioxide is evolved, our flask would get lighter and lighter. So here you'd see that at the very beginning of the reaction, the mass is the most and it decreases. Right, so it decreases rapidly at first, and then just a little bit at a time until it stops. So what factors affect the rate of reactions? We have surface area of the reactants, concentration of the reactants, temperature at which the reaction is carried out, presence or absence of a catalyst, and light or pressure, but that is only for certain reactions. So the first factor is surface area. Now let's say, for example, we want to investigate how fast sugar dissolves in water. We are given a cube, we are given granules, and we are given powdered sugar. Which one would you expect to dissolve fastest? Now, from your knowledge, you know that powder will react the fastest, but why? So larger solids have a smaller surface area. Reactants have less surface to interact with. So look at it here. This will represent water molecules trying to hit against the sugar cube. Right? So there's actually less area for the water to interact with. Smaller solids, however, such as the powder, will have a large surface area. The reactant will have more surface to react with, and the reaction will take place faster. The second factor is concentration. Now let's imagine these two boxes here are two separate vessels which have a reaction taking place. In this vessel, we have an acid and base that are both dilute, and in this vessel, we have concentrated acid and a concentrated base. Now if you look here, something that is dilute, of course it has more water and we have less molecules, less reactant molecules. So a lower concentration will have fewer reactant molecules, and of course if you have fewer reactant molecules, you must have less successful collisions, which would result in a very slow rate of reaction. Because let's say this white part here is water, the water will be getting into their way. Now at a high concentration, we have more reactant molecules, which would result in more successful collisions and a faster rate of reaction. So we know as we increase concentration, we will have a faster rate of reaction. Our next factor which affects rate of reaction is temperature. Now, all molecules have kinetic energy. So at a low temperature, for example in this one, they will have less kinetic energy. At high temperature, they have more kinetic energy. So if these reactant particles are taking their granny time to reach the other reactant particles, of course, it will have a slower rate of reaction because there are less collisions taking place. Now these are the speedsters. At high temperature, they will be moving fast, crazy, fast and furious, right? And they will have a faster rate of reaction due to more collision taking place. The next factor affecting rates are catalysts. What exactly are catalysts? Catalysts increases the rate of a reaction without itself undergoing any change. So a catalyst is essentially like the tinder of chemical reactions. It brings the reactant molecules closer, faster. Right? Now one example of this is enzymes. Without enzymes, all these reactions taking place in our body will take place so much longer. Alright, so the enzymes help to speed up the rate of a chemical reaction. We also have catalysts in industry, right? There are many chemical reactions in the industries that require catalysts because simply it reduces the amount of energy for the reactants to actually react. So if you look at the energy profile diagram here, reactants and products have the same amount of energy, However, the amount of energy it takes to cross the activation energy is different. A catalyst lowers the activation energy required for any reaction. I also like to compare it to frying plantain. So sometimes you fry plantain and then you look away, and when you watch back it burns. Sometimes I think of looking back as the catalyst to my plantain frying. Our next factor is light. Some chemical reactions are affected by light. When particles absorb light energy, the energy can be used to break bonds, overcoming the activation energy of the reactions and causing a chemical reaction to occur faster. Reactions which occur as a result of the absorption of light are known as photochemical reactions. The absorption of light in these reactions causes bonds to break, producing reactive particles known as radicals. For example, when we use aerosols like bug spray or hairspray or anything like that, it releases something called CFCs, or we also call it chlorofluorocarbons. Now, when they are in the atmosphere, they are inert and they do not react. However, when it reaches the stratosphere, the high energy UV radiation breaks the CFC molecule, as you see here, right? So this is chlorofluorocarbon. UV light causes it to break and form another chlorofluorocarbon and a chlorine radical. So this chlorine radical reacts with ozone, which is O3, which is our ozone layer, and it forms these products. So it breaks down the ozone layer. If you look here, this is an actual hole in the ozone layer, right? So what we call greenhouse gases, these things break down our ozone layer using UV light from the sun. Light is not always an important factor when it comes to rate of reactions. It is only necessary in terms of photochemical reactions, which are reactions that are only sensitive to light. The next factor is pressure, and this applies only to gases. So here we have two vessels, one with regular gas and this one where we compress the gas. So here we have a number of gaseous molecules. The molecules have more space to move around and there is less chances of collision. When we compress it, we give them less space and it increases the concentration. Therefore, they are more likely to collide. So let's just wrap up what we did previously. So we know that reactions can take place at different rates. In order for reactions to occur, it must follow the collision theory, which states that reactant molecules must collide with enough energy, also called the activation energy, and with the correct orientation. Different factors influence the rate of reaction. Those include concentration, catalyst, pressure for gases only, temperature, particle size or surface area, and light. So light and pressure are for only certain instances. So that's it for today. You can look out for homework on Edmodo and also look out for a second video where we will explain graphs and their shapes. That's it for today. Bye.